Okay. Let me just. Yeah, can you guys see the presentation?
Yes.
Cool. Oh, great. Okay, it's a bit echoing, but it's fine. Yeah, so the paper we are going to discuss today is called Nested Learning, the Illusion of Deep Learning Architecture. It's a paper from Google Research. I found this paper really interesting. Like, I also saw a lot of discussions in the community about this. And that's why I picked this paper. This paper is basically like challenging the real meaning of intelligence, which we will look into. So let me just get, yeah, sorry, just set up something. Yeah, sorry, yeah. So this paper speaks about how we see deep learning. We usually see deep learning as stacking multiple layers in a model, but this paper challenges that it's not necessarily like that. Well, we can see the machine learning system as different components. So I think it's really fundamental research. It can be groundbreaking research. It will possibly unlock artificial general intelligence. So that's why it's very interesting to discuss. Yeah, if anyone wants to have comments, anything, correction, just shout out. I'm no longer expert in this paper, so hopefully it'll be more like discussion than me presenting. Cool. I will start with what are the high-level ideas that this paper discuss. Mainly, the key challenges that this paper is trying to solve is first about catastrophic forgetting. Most of us knows that this is one of the most crucial problems in machine learning, that the model will tend to forget what it already learned way in the past. And definitely with LLMs, as we've seen with long context, the LLMs will basically like forget what if the context is really long. And second point, which is really interesting, is that in traditional machine learning training, once we stop training, the model will not learn again. So there is a clear distinction between training and testing. Once we stop training and deploy the model will stop learn. If anyone has read or heard about Titans, this paper was written by the author of Titans, which basically introduced this kind of concept that is learning during test time. So this paper is basically like the continuation of Titans. And the next bit, I think there is noise. I don't know if can someone like mute themselves in the like.
Oh, sorry, I forgot.
No
Oh,
worries.
sorry.
No worries at all. Yeah, this paper also challenges about how learning can be very inefficient in traditional deep learning methods. For example, we tend to stack more layers if we want the model to learn more complex patterns. But in the end, the model didn't really learn better having deeper layers. So there is a particular like limited computational depth even if we keep stacking layers. This paper also challenged about the use of optimizers. Usually, when we design the machine learning models, we see the models and optimizers as two different entities. We didn't really think about like how certain optimizers will behave differently given like different model architectures. But
Yes,
this
I feel
paper,
that already.
yeah. So yeah, this paper will see this kind of problem in a different way. Okay. And what is the main concept that this paper introduced? I have to say, like this paper is quite long. It's like 50 pages, excluding the appendix. But to me, like the gist of this paper is basically saying that deep learning is not just stacking layers, that basically all the models components, including the optimizers, are just different components. They are uniform components, and they update and share data at different frequencies. And this is the idea of solving the problem of catastrophic forgetting and continually improve how they learn. Yeah, I have to say that because this paper is really long, we might not be able to get into the details of every single bits. Yeah, we will see depending on the, hello. We will see depending on the discussions, and we might want to skip some parts. Yeah. So the main contributions of this paper is first that it introduces new paradigm to see neural networks as components, as mentioned before, that basically the model architectures, the optimizers, they're actually basically components that interact with each other at different frequencies. And using this concept, they introduce some other new kind of way to make more efficient learning. For example, by having more expressive optimizers, by having self-modified learning module, continuum memory system, and continual learning model called HOPE. I know it will sound a bit weird what it is about, but we will go deeper on what each of these means. Yes, Arshad.
Yeah, so is it fair to say that this paper is kind of really taking what the brain, the biology the brain is doing, and kind of trying to replicate it? Or is that like too simplistic a view?
I get what you mean. I get what you mean.
Yes, exactly. It got the inspirations from how brain works, and it basically challenges how we have been designing neural networks based on that neuroscience knowledge.
Yeah, that's great. Thank you.
Yeah, we will look in a bit. Basically, that's the next bit of this presentation. Before we go further in the paper, let's revisit how our brain works. So,
yes, this is interesting.
What makes our brains great? First is that our brain has a feature, capability that we call neuroplasticity. It's basically the way that the synapses, the neurons of the brain can form new synapses based on the new information that we receive. So it means that every part of the brain is a uniform components. We can see, I think I read on the paper an example that if someone had like a brain injury or something like that, basically the brain can sort of relearn because of this neuroplasticity capability. And these different brain parts, they oscillate at different frequencies. Yeah. And this
very annoying. That's why I asked stop, because it's not.
Can someone? Okay, we need to stop the. It's too much emoji.
Yeah, stop.
So
I'm sorry. I'm sorry.
Yeah, so with different brain components, they operate at different frequencies. There are part of the brains that receive like more information more frequently, but it means they have a shorter memory. But there are other parts of the brain that they have like they update the information, they update their knowledge less frequent, and this is how they can retain the memory longer. And how these different parts of the brain communicate makes the whole human memory system, the short-term and long-term memory. And this is the inspirations that this paper is implementing. Yes, please.
Oh, sorry. I had a question. I wanted to ask, like, it's my first time in these meetings, and I wanted to ask, how do you know all this? You study?
Sorry, what do you mean?
Like, you study this, or this is from AI ChatGPT?
This is like, I mean, like we read this paper and then we have discussion.
Oh, okay.
Sophie.
Sorry, that was a very rude question to her.
Yes, I was going to say,
What?
this is a paper club for people who are interested in machine learning, and we have professional machine learning engineers who have studied at like master's level and work every day. Usually we like to try and have constructive conversations, but if things are too distracting for the speaker to speak or to have these conversations, and we will have to take actions to block you attending for the rest of the session. I'm sorry to say, but this is getting quite distracting.
Yeah, thank you, Sophie. And yeah, let's continue with the discussion.
Were you talking about us? About me? I was just asking a question. I don't know.
That's fair for now, and so I hope we've been able to help a little bit. But from now on, just so you know, we'll go from there.
Oh yeah, thank you, Sophie. Yeah, so there is a common brain disorder. It's called anterograde amnesia, where someone learns about something during a particular period of time, and after some point, then they will stop learning. And we can see that this kind of phenomenon actually happens in machine learning. So it happens in LLM. We can see that when we train LLM, it learns a lot from a lot of like multiple different corpus. And then when we stop learning, when we stop the LLM training, then the knowledge in LLM didn't increase anymore. We can use this LLM during inference, like introducing extra context, but it doesn't mean that it will change the inherent knowledge that LLM has learned during training. And there was a period where LLM basically didn't add more knowledge. So we can see that this is similar problem we have with LLM, and this paper basically tries to solve this problem. So, okay, inspired by that, this paper introduced a new training paradigm called nested learning. And let's see what is actually nested learning. Yes, we spoke about basically instead of seeing the machine learning model as a separate entities between like different models, different optimizers, we see that this is a system consisting of different components, and every component has its own internal gradient flow. Basically, in simpler words, is that every component like learns. There's some learning process in every component, and then in a bigger system that the learning between, so the learning of each component like can be transferred. There's a communication between the knowledge. So there is a communication between the different components regarding the knowledge that they have learned. And this way we can see that basically all machine learning problems are nested optimization problems. We can see that, for example, I think we will see in the next bit. For example, if we have like gradient descent, we learn, the optimizer learns how we can find like the best like weights that has that that will give the minimum loss. But if we introduce like momentum in the gradient descent, there is another layer of optimization where basically we want to find how much gradients we want to take into account. Yes, another layer of optimization. Yes, please.
I'm learning so far. Thank you.
Okay, so we remember about what we have discussed about how our brain works. This is basically a comparison between the brain and how nested learning sees these configurations. Yeah, basically in our brain, there are different sections with different frequency updates. Same with nested learning, we see every component of the whole systems as different components with different frequencies, and then they will communicate with different frequencies. If we look at this picture on the left side, on the top, sorry, top left, this is how we traditionally see a deep learning system. For example, we have a sequence of blocks like RNN, attention. We can stack different kind of models, but here we don't see how to say, like, we see all components as one layer. But if we go deeper, sorry, can you please unmute yourself? Thank you. If we go deeper, we will see that actually every component here, like RNN block, attention block, it has its own gradient flow. And it is a nested optimization process as we have mentioned before. And this is how now we can see this whole system. Yes, please. Anyone has their hands raised? I'm really sorry.
Yeah, Inneke, you a fucking bitch. Inneke.
I think they just need to kick these people out. Thank you, Nami. Cool, yeah, thank you, sorry. Thanks everyone for handling this. I'm really sorry. I'm sorry, I got quite distracted. So yeah, let's just revisit like some common terms that this paper spoke about. I think it's good to know what it means before we go further. One term that they introduced is called continual learning. It means that like I would say like a model where we can continue to learn from new data streams. So this is something that this paper wants to achieve. And another term that they use a lot in this paper is called in context learning. There are a lot of definitions of in context learning, but this paper in particular, they define in context learning as the ability of a model to adapt itself to learn from a given context. Basically, pre-training is a form in context learning such a way that the context is the data and basically want to compress that context into the model's parameters. So that's why it's called in context learning. The next one is about learning versus memorization. It's basically like taken from neuroscience definition about what is the difference between learning and memorization. And the definition here is that, oh, sorry, it's a typo. Neural memory is a neural update caused by the input. So basically a form of storing information. And learning is a process of acquiring effective and useful memory. So it's basically a operation of the mapping operation, like given something, acquire something. So if we say it's effective learning means that we have an effective mapping process or mapping function to acquire the information given the key, basically. Maybe that's more machine learning term. Yeah, this is what we just spoke about. It's particularly called associative memory, and we will see that basically the whole learning of machine learning process is similar to associative memory. It's basically want to know that given the data, what is the like given the new input, what is the basically the ways that weights are given that gives the highest gradient, hence the smallest. I hope I said correctly. We will see that in the next slide. Yeah, okay. So because this paper, basically they use some basic knowledge, like basic theories from machine learning. Let's just refresh ourselves on that. Like first about gradient descent. Just a refresher that gradient descent is a form of optimization where we want to find, like in every single step, we want to find the steepest gradient in a loss function. We want to get to the local minima, and then basically we want to find what is the path that will lead us to the local minima as soon as possible. In other words, we want to find the steepest descent to that. And the second concept is meta learning. That is basically we have two-level optimization. So there are two models. We call it like outer and inner models, where like the outer model learns a set of parameters, and the inner model will use basically like this learning from the outer model to maximize the performance on a task. So we can simply call it like learn how we learn. Like we can see it is as example where the model can learn how it can learn better on a new set of tasks. The third one is linear transformers. The idea of linear transformers from associative memory points of view is that we store key value pairs, let's just call it K1 and V1, in a memory, and we want to retrieve the value V if we give a particular value of K. And sorry. And we can see here that it's again two level of optimization process. Like the first level, we learns the values of the parameters, and then the second level is that we want to learn like how we store these values, because we definitely cannot store everything, and this is the idea of like knowing which information to store, which information to get rid of, and how we retrieve this information. So this idea like fits the concepts of nested learning that is introduced in this paper. Okay, I think this is a lot of introduction, but basically, in my opinion, like all of the ideas of this nested learning really heavily emphasis on all of these background concepts. It's just like this new paradigm sees different way, and we will like expand this idea to a more to like a higher level. Yeah, okay, let's just then now have a look on like just the normal MLP multi-layer perceptron training with backpropagation. As we know, it's basically when we train a machine learning model like MLP and with backprop in particular, basically want to find the change, sorry, like in every step we have a set of parameters, but we want to find in the end the most optimum parameters that give us the smallest loss. In other words, we can say basically in every step we want to find a mismatch between the current output and the objective loss. So basically, like the difference between the current output and the target, we will say sorry, how to say, like the difference between the current output and the target, basically we can see it as the surprise of the model. I find it something's a bit weird to see as a surprise, but I can see like where this paper come from. So the idea of this, the idea of this is like we can see this situation, this problem, as an associative memory that maps each data sample to the error. So the whole system, the whole training is basically finding the good mapping, like building the associative memory that maps the data sample to the error. And if we look further on gradient descent, we talk about basically the gradient descent is the idea of finding the steepest path on the loss of function. And most of us know that another version of gradient descent is with momentum. It means that we want to, because also like if we only take into account the steepest path on the loss function, we might end up with like oscillating values, because in order to reach the, maybe like there is the path that has the steepest gradient is not necessarily going straight towards the local minima. So the idea of having momentum is that we want to see the general trajectory to the local minima. So it's sort of a form of low-pass filter, because it basically smooths out the, how to say, like the change in gradient if it's like a zigzag kind of path to the local minima. And with momentum, there is a parameter on how much of the past gradients we want to take into account to determine the general trajectory to the local minima. So we can see this as a two-level optimization problems, where the first optimization is to find the gradient, but also another level of optimization where we want to find the coefficient that controls how much should we take into account of the past gradients, like how far should we look back of the past gradients to get the next gradient. So again, all of this, the idea is about multi-level optimization problems. And then same if we see like a linear attention that we spoke before, it's also a two-level optimization problem. And we can imagine that if we train linear attention with momentum gradient descent, basically it now becomes like 3 layers. So everything can be seen as different layers of optimization problems with different frequencies on when the parameters get updated. Yeah, so the whole thing that we have spoken about is about we have been talking a lot about the frequency, like different levels of optimization, different components, and how they will like update the parameters and like share their knowledge to other components, which is the first one. And the second one, which is very important when we also want to design this kind of nested learning system, is also how the knowledge will be transferred between levels. So for example, like the every component has their own parameters, but then they need two components to use these parameters, just like in the meta learning paradigm. Yeah. There's a few so definitions here related to this design choices, which again is basically a lot of repeated information. I find this paper, but I think it's good because there's a lot of new concepts here. So when we say components in the same level, it means that they have the same frequency updates. And the higher the level is, the lower the frequency. And mapping this back to how our brain works, it means that the higher the level, the longer memory that it will store. Like the faster it receive information, or in other words, the higher frequency, it means that it will have a shorter term memory. And with this nested system, with a lot of different components with different frequencies, they do not necessarily have to dependencies between them. They can stay as a standalone, like individual component. So there is no, I would say, like rigid, defined ways to form the dependencies, because we need to see them as like a separate, uniform, independent system. And we can talking about the associative memories, the fact that basically memory is a way of mapping keys to values. We can also see this as a nested system with different frequencies and different communications, which we'll discuss in the next session. In the next part of this presentation. But they are also like an individual, independent component. So yeah, as we have discussed, every component has their own frequencies, they can update each other, and there must be a way, like the different ways of knowledge transfers between the levels of the, between the components with different levels. I wouldn't say we should spend much time in it. I don't think the paper also put a lot of emphasis here. They just highlight that there are a lot of ways, like several ways to define the knowledge transfer between levels. It can be just a direct connection where the components with higher frequency updates the other components with lower frequency. Another one is when the one component parameters are treated as the other component, another component's hyperparameters. Yeah, or we can, or they can, like one component parameters can be updated on the same flow of gradient, but different frequencies, something like that. Let's just not. Basically, here I just want to, this paper just want to emphasize that it doesn't matter what sort of knowledge transfer that the different components communicate. The idea of this paper is that it's basically very flexible, that we can have multiple different components with any sort of knowledge transfer, and we just, and basically during the design a process of this system, it's something that we need to take into account. So now, like looking back at it, it's like we normally see the optimizers as a separate component from models. We see like models is the architectures, optimizers is a completely different thing. But as we have seen before with the gradient descent, basically optimizers is also something that learns something. It learns how it compress the information of the gradient to its parameters. So optimizers actually suffer from similar problems like the actual model itself. Like with LLM, for example, it suffers from long context that it will forget. It will have like catastrophic forgetting, where it forget the old knowledge. Optimizers also suffer from the same problem. Like in gradient descent, if you think about it, the aim to get to the local minima as fast as possible. It doesn't take into account the fact that it might forget the lost surface, the lost, I would say lost, I completely forgot how it's the right term. Like completely forget, sorry, like it doesn't really take into account how, like the trajectory in the past. It's just focused to get to the local minima. It means that it might forget what it has learned, like the old information. Especially with this momentum, it will smoothify the gradient updates, and then it means that it will forget a lot of like the details, like the oscillations in the loss curvature, and that's the better word. So the idea with this nested learning, which I really like, because it will see this optimizer as a learning model as well. One of the ideas here is to find optimizers that also retains information from the past. And this is where they introduce delta gradient descent. So when they update, when this kind of optimizers update the weights, it doesn't only take into account the fact that where we can find the steepest gradient, but it also incorporates the previous state of weights. And why is it important? It's because if we change the weights a lot, it means that we change the model's inherent knowledge a lot, and we don't want that. Like, we want the model still retains the old past information that was like compressed in the previous state of weights. So having optimizers that also incorporates the previous state of weights means that hopefully we will retain like more information from the past. It doesn't easily forget. So this is intuition. It's really, I asked ChatGPT, give the easiest intuition on this. It's like gradient design is really focused to move weights in the negative gradient direction, but for delta gradient design, we want to keep it like not deviate that much from the previous or the latest weights. So I think there's a lot of things we have discussed. So let's just recap the key concepts of this paper so far before we get to the last, I would say the last concepts, the last architecture that they introduce. So this paper sees the machine learning models and its components as interconnected system. It doesn't distinguish between models, optimizers. It sees everything as a uniform system with different frequency update. Hence, the optimizers are also learning modules. It's just the difference between optimizers and the models are more about the data it stores in the parameters. The optimizer stores the gradient, put the gradient into their context, stores the information about gradients in their parameters, while the model architectures, the model itself, stores the data, the information on the data, on the parameters. It's just a matter of what sort of data you want to compress, but both are learning modules. And they have different frequencies updates, hence different levels. And it means with all of this paradigm that there is no clear distinction between training and test time. It will see just two different states where it receives, when it receives information as input or when it's just an isolated learning system. Because even during test time, that the model can adjust their parameters based on the new data coming. Okay, so with all of this bunch of concepts, they design what they call Continuum Multi-Timescale Memory Systems, or CMS, which is, to me, simply speaking, instead of just stepping back a bit, if we remember in transformer architectures, we have the attention blocks, mainly are the attention blocks and the MLPs. I'm not talking about the other like encoding or page norm, something like that. And we can see in that kind of architectures, the MLPs become the memory of the model, but it's just one single MLP. This paper basically saying that having a chain of MLP blocks as the memory component of a model will help the model to retain longer memories. Yeah, and I think I want to show that. Oh, I remember this in the later slide. So basically, the idea of having a chain of MLP blocks is that different components, again, different blocks, they learn at different frequencies. They retain information at different time scales, and this is how we can keep information from the past. And in transformer, we only have one MLP block. Hence, if we forget something, basically we will forget it. There's no way to regain the information. And Yeah, because we now have a chain of memory blocks. There are a lot of ways on how these different blocks can be structured. They can be like sequential, they can be nested, just the same idea like the knowledge transfers. Like there is a different, how to say this is part of the design choice. But yeah, again, to me, the emphasis is that it's all flexible. This paper doesn't suggest a particular best way to structure this, but it's just give us like the ideas on how we can arrange these components. But something I want to highlight here, because I find it very interesting, is that because I was wondering when reading this paper, okay, now we have a chain of MLP blocks that act as the memories, but how does it help with catastrophic forgetting? And the idea here is that by having different components that retain information at different frequencies and different time scale, we sort of have like a redundant memory. So if a block forgets something, like the higher frequency blocks forget something, because remember the higher frequency means the shorter term memory, we have the longer term memory, which is the lower level, which is the higher level component where we can where we can obtain back the information from. So that's the idea. By having, like, basically to me, I see it as a redundant memory. There are components that can retain information longer. There are other components that learning fast, but they easily forget. So when these components basically forget, we have this sort of other blocks that have longer term memory where we can retrieve the information. This is how we solve the problem of catastrophic forgetting and basically enable continual learning. Yes, Arshad.
So this sort of sequence of MLP blocks, where they're saying that the nested sort of like gradient optimization step goes on each individual MLP, or is it still end to end? But it's just the kind of maths of it that works out that because there's so many dimensions that you don't the forgetting aspects coming from that. It's not actually changing the weights like on a different schedule.
Sorry, it's the question. Sorry, I didn't really get the question. It's the question about.
So we had this kind of nested set of MLP blocks, which they're saying is this memory. Is that correct, first of all?
Yeah, this is like one example of how we can stack these different MLP blocks.
I just wondered, the updates for those, are they all using the same kind of gradient update, or are they kind of, there was that nested thing where they were like kind of working out the parameters for how to change the nested model? Is that being used here, or this is all still just one set of MLPs with some nonlinearities in between?
They have their own gradient updates by having their own contact flow. That's my understanding.
Okay, that was my question. Great, thanks.
Yeah. Thank you. So yeah, my understanding here is that every component can have their own context flow. Like that's how they can retain and like learn different way, and they just like transfer the knowledge between different blocks. Cool. I think one thing that I also want to highlight, like in the paper, they challenge if now we have like a lot of different blocks, and does it mean that we will like basically the train will take longer? And they claim that the learning can be paralyzed. I wouldn't go further into it. Like I don't think they also explain more about it, but basically they claim like it will not hold up your training by having like more blocks to train. Okay, with all of this ideas, they come up with this new architecture called Hope. To me, basically, Hope is just a summary of everything. The fact that we now have different components like multiple MIP blocks that form chain. Now we can see this as like a big system. That's basically what Hope is. And I would like to me, it's easier to understand something if we know the intuition about it. So to refresh our memory on transformer, like the main problem is that transformer will just like, you know, the normal attention, it will look at every single tokens, and then it will see which of the tokens matter. That's why it might be like it will easily hit the context length, because the more tokens it see, the more it will see, and then we will hit the limit. And then it also will be static, because it will only see what it has, what the information that is given to them at that particular point of time. With Titan, yeah, I remember a few months ago we had presentation about Titan. So the idea of Titan is that during task time, during inference time, the memory will can also be updated, and there is a mechanism to tell that, oh, this information is not important, I can forget about it. This information is important, I will keep, and this means that it will be able to remember like more things from the past. And with Hope, it's basically adding another layer of Titan, is that Hope will learn how it learns. So this is the meta learning comes from. It's like, okay, now I know that I need to update my memory, but now I also want to learn how I should update my memory so that I can keep what is important and not. So having said that, basically Hope is Titan with multiple levels of components. We don't have much time. We only have 3 minutes left. So I think the last important point here is, yeah, to basically see that what Hope actually means. We basically already speak about it. They claim it as a self-referential Titans, means that the model can generate its own values. So during inference time, in attention, like all the keys values or the parameters basically are static. We don't relearn their parameters. But with Hope, those parameters keep updated. It means that, yeah, it will always learn as the new data coming, and it's multi-level optimization process as we saw about. So it means that it will like enable this continual learning. I think that's the main key. The scaling Hope is just like the manifestations, all of the concepts they introduced in this paper. Yeah, I didn't read much about the experiments. So basically they say that Hope outperforms like all the baselines on the continual learning. Like I think it's translating languages, but basically, yeah, they just claim that it's it performed the best, and with more levels, the performance also gets better. Yeah, okay, this is the last thing, so it's just last minute here. Back to the initial question, this paper tries to solve the problem of catastrophic forgetting. So is catastrophic forgetting solved with this nested learning? They claim that it's not solved because it's an inherent problem when learning, right? Like even as human, we have capacity on how much information our brain can retain. So it will still be a problem, but this nested learning is a way to achieve like a longer memory, like longer training by decomposing the systems into different components. So yeah, they say it's just a roadmap rather than destination. And yeah, that's all for today. Any more questions and concerns? I'm sorry with the distractions also earlier today.
This is an amazing paper, and I have so many questions, but I also feel like I want to think about it a bit. But just the different way of thinking about it, I really enjoyed. I think that's really made me smile and really made me, I think, be thinking about it for a long time.
Yeah, thank you, Sophie, for handling them today. Yes, Arshad.
Yeah, so I mean, I only sort of skimmed the first bits of the paper and then the results. And as an idea, it's obviously amazing. The only thing I didn't like, which I guess they can't help, is that the evaluations were on really weak LLMs. I think their models like 2 billion parameters or something like that. So I have asked Ali if they've done any sort of results since then on stronger LLMs comparing it to this is doing, and whether the scaling laws still apply. He hasn't responded, so we'll see. Yeah, amazing, and thank you for presenting it. I know it was a bit of a challenge at the beginning, but yeah, it's an amazing paper. Yeah, thank you, and please share any response to the Discord because I'm also curious. Cool. Thank you again, everyone, and see you in 2 weeks. Bye.
Thank you so much. Bye.
Thanks. Bye.